Yeah, ray marching. Yeah, so yeah, looking at ray marching stuff here tonight. That usually refers to sign distance field type of stuff. So that refers to a specific way to get an intersection with the surface. It's kind of a successive approximation of the surface. You kind of move closer and closer to it as you go along the view ray. So you can we'll talk about how that works, but yeah, if you take enough steps, you get close to the surface. That's where your distance from the surface is zero, or close enough that you consider it less than some epsilon. So you call that like yeah, you call that you hit the surface basically. Um, so anyway, yeah, so analytic ray intersections deal with more explicit um, arrangement of shapes. You have like triangles or spheres, and that you solve some quadratics or whatever it is to get an exact intersection with those primitives. But you have to evaluate all of them or deal with some sort of organization scheme to make that faster, basically. Uh, so what this does is it's a single function that you just the return value is um, how far away you are from the surface at any given point in space. So this is called an implicit definition of a surface. And sorry, basically, yeah, you don't get that exact value. You have to take successive approximations until you're close enough, because you won't always get exactly to zero. Um, whatever the situation is. um, yeah, so they've got some different types. Talking about rasterization also, so that's another way to produce the same kind of results, I guess, in terms of representing surfaces. Um, so I guess the function g is their distance function. So you're looking at steps along. Um, hmm,
I think this is just the uniform step, right?
okay, yeah. So they are taking it, yeah, just the uniform step there. Yeah, and there are some rendering methods that use that. Yeah, somebody I talked to, they do sort of a and a lot of the ones that you see on Twitter, the minified GLSL stuff, that a lot of those kind of what they do is they add the exponential of um, the distance function return value as a color, and basically accumulate it as they take steps through the space there.
Well, we don't need spoiler. It definitely will be covered below.
Yeah, right. Yeah. Anyway, then yeah, but the idea is yeah, taking the getting the distance estimate from the surface. You know how big a step that you can take without possibly intersecting, even if you were going directly at the surface. That's like the closest possible intersection point with the surface. You know, you can take that largest step. And some of them don't give that good an estimate, so that's kind of, you know, where you get as it is an estimate, I guess. And as long as it's a lower bound, um, like you don't get a surface that's any closer than what that function returns. then you're fine. But it's when it's the opposite, then you'll step into the surface basically.
So you always want your step to, or the estimate to give you a smaller distance than in reality, right?
Yeah, and so what you can do, and this is something I've been doing, and depending on what kind of amount of time you want to spend on it, you can multiply that return value by some constant between 0 and 1 as like an understep sort of thing.
Oh,
And
just to make sure it's always going to be less.
right. So you have to take way more steps, but you can get a much closer approximation of the surface. For some of the ones that don't, hold that distance value thing very well. Yeah, so that's kind of what they call sphere tracing. So you're if you've seen visualizations that I'm not sure if he has any in here, but
I think they have a visualization on that page.
this idea
Yeah.
of spheres here. Yeah, and basically being able to take these steps of a certain distance. Yeah, you basically you take successive approximations towards your surface intersection point, and until you're happy with that return value. Is kind of the idea there. And what's cool with that is you can take the gradient of that function that defines your distance to the surface, and from that you can derive the surface normal. You can take the gradient of that space and basically the direction in which it is increasing distance away from the surface. That's where your normal is pointing. So you basically just take a weighted sum of a couple of samples nearby in the function is a good way to get that. I also have, I can link it in Discord later. The
I think
DEC
maybe
thing
let's
on my
wait a
website.
little bit and see if anyone understands the above code. Just like if anyone has
Sure.
preference with the sphere tracing
Yeah,
code,
yeah.
because that's the most important part.
Sure. So here's an example of distance to a sphere. You've got basically the length of the vector from your sample point. I guess x is x to the sample point. Yeah. So yeah, the length of the vector, that's the displacement between the center point and the location, which is basically the distance between those 2 points, minus some radius, because we know that the point x you're going to be within r distance of the center point.
So I guess
Planes.
then
So,
this also gives you the negative distance, right? If you're inside.
right, exactly. Yeah, because then r would be greater than the distance between those 2 points. So that number would be negative.
That's why it's called signed distance function, because negative means inside.
Right.
Yeah, so that's continuous through that surface. It crosses 0 at the surface. Yeah, so plane distance is similar. You just take the dot product of the displacement vector, and if it's that perpendicular to the normal vector, then that should be n. Yeah. Anyway, yeah, that's you take the dot product with the normal. It's the There's a typo there. But anyway, the yeah, so dot product is 0 when you're at 90 degrees, and then negative if you're going to be at an obtuse angle with the normal vector. And yeah, so I guess that's just going to be a yeah, it'll be negative if I guess you're on the opposite side from the normal vector.
And I guess that's a infinite plane, right?
Yeah. So yeah, like what is it? 3 points to find a plane or something like that. Anyway, yeah, it's like, or like a normal vector.
Yeah.
Anyway,
it's
yeah,
3 points
it's
or
just
point and normal.
So is it really infinite? Because like, doesn't the C? I guess it is infinite, but it's like weird that you have this C. You really only need like the normal and one scalar value or something.
I feel like, yeah.
Well, you need a point on the plane. And then the normal, and C is supposed to be a point on the plane. I believe. Or maybe that's supposed to be X.
Yeah, I
That's
think
probably-
maybe this whole equation
That's
is
probably
wrong.
the offset. It's probably the offset on there, because if you have the plane there, you're going to have some offset from the normal where it's located. So you can imagine a plane being, centered around 0, 0, 0. But if you move that up or down, you'd have to have the offset for it. So I bet C is probably the offset for the plane.
Yep.
Yeah.
So like,
Yeah, it might be minus C on that. Is it? Or
I guess it's okay.
Oh, C
Yeah.
could just be any point on the plane though, right?
Yeah.
Yep.
Hmm.
Yeah, I guess the dot product works out the same way.
I guess it simplifies or something. I don't know.
And then-
Yeah, so go ahead.
Nothing. Sorry.
No.
Did they talk
yeah.
about the like min and max using that before this point? Like using that to combine SDFs?
Oh no, yeah. Well, so when you take the minimum of 2 side distance fields, it means you're looking at the minimum distance of 2 different ones of these functions, and so basically you want the closest surface hit, closest surface distance. So you're taking the minimum distance between the 2 return values, if that makes sense. And then there's other ways to combine those. I'm working on a good way to present that, like a larger
I
collection.
think it's like visually it's like union and the intersection.
It's like set stuff, but yeah, they do it with like mins and maxes, or like the maximum of the negative of one from another or something like that.
Yeah,
the
I see
unions of point.
they do actually talk about it later. I just noticed. So
Okay, yeah, I haven't looked ahead here. But yeah, so some of these, you can go through the derivation, I guess. Maybe they get more complicated from here. So yeah, if you're interested in the geometry and stuff, like it's cool the way that they derive the distances on some of these, like and some of these are there's ways to project like things onto a cylinder, and people do stuff like on the surface of a cylinder that's mapped with a u and a v that they solve for. So that's pretty cool. And they can get that from that same function as they're doing the math for the distance. So anyway, that's something cool that they do with demo stuff sometimes. Yeah, and so this here is talking about that, solving for the gradient of the space, to get yourself a an estimate of like in which direction the density or well, whatever you want to think about it, like the value increasing. You want a vector pointing in the direction in which the value is increasing most strongly. So you take an average of several points near this point, and then you can solve for an average vector, weighted by return value. And the more heavily weighted vector in there, basically it averages out, and that works out. So yeah, you basically just take some offset vector from each of these, and then I guess yeah. Yeah, and then normalize it basically to get yourself a unit vector for the normal. So yeah, there's a couple different ways to do it, I guess. So yeah, I guess setting up a camera here. And all the ray setup stuff. We've gone through that before. I don't know, we can go through that again if we want to, or I don't know if we want to. There's a lot of different ways to set up your view rays. Anyway, yeah, so yeah, you basically, when you want to trace array for your okay, yeah, so yeah, the function that tells if you hit or something, yeah, you're basically you're starting with your point and your direction that you're tracing in, or rather W is that. Yeah, and I guess they're doing a couple different things here. Oh yeah, so that's maximum distance, I guess, in the scene. So yeah, basically you start with a large distance before you check the scene distance, and that's just so well, okay, if you do anything that like, well, anyway, yeah, it's funny errors happen when you have like global state with this type of thing, or like, you know, any kind of stateful thing. It's kind of interesting sometimes. Anyway, once you get the maximum step size from the scene distance at that that direction vector times your step size, which I guess is initially 0. So this is just sampled at P. So we solve for dt, and then we add to that distance along that view ray, that maximum distance. So if we say if that's a surface hit that's below some value, then we do our surface calculations and we say that we hit it. If we don't get that and we've exceeded some maximum distance, then you know, we're not considering that to be a surface hit. We're just saying that this is false. We didn't hit anything. Anyway, so yeah, and then you just continue through this loop until you know, hit one of those situations or you fall out, and you say that you hit
I
the
don't understand
skybox.
how the distance seems to be updated in the loop.
Oh, weird. Yeah.
It seems like a bug. It should be in out or something.
Yeah, it says it's in out. So
Oh, it does say in out. Yeah, that's correct.
Yeah, that is a little strange.
So they're like calling trace array once for each object instead of using min max, and you know, like having one scene distance. That's what it seems like.
Yeah.
I think it's just the one scene distance, right?
Yeah, but he's saying like it's the line 18. If you've hit something that's closer, then you should just stop.
Okay, so I guess that's the.
I guess, I mean, you can combine those, like, do the, repeat, like iterate over multiple groups, and each group has multiple objects in it.
So for
That's
the
interesting.
SDF, it's different from like maybe in normal ray tracing. You don't actually have multiple objects. You like using a primitive like min and max to combine everything into a big
Mhm.
kind of like same distance function. There are use cases for like having multiple SDFs. Like for example, for my planet stuff, I did unshaded toy. I did one SDF for the planet, another for the water, but usually we just have one.
Yeah, and you can check like, yeah, if the Boolean combination of these two is the same as the Boolean combination of, or just the one input by itself, then you do this kind of surface behavior, and if it's not, then you do something else. So you basically just check if that's the closest point out of the set of objects that you checked. So you can change the surface behavior based on what you hit between the combination of several of these things. This is kind of interesting the way they did this. I guess they passed it in as a maximum distance, but then it comes out as the closest surface distance.
Yeah, I don't really.
Or the distance.
And why is like if in
I actually
the
kind of like
else if
this.
case, like when it says else if t is greater than distance, why do they then return? Because then they'll never reach that infinity stuff down below.
Well,
Either that, or it was just the last time that you added the distance. So it's kind of,
Yeah.
well,
I
if
guess
it gets,
how
it's
far you
for
want to go
handling
under it.
multiple SDF, or like if you want to plug in this into a ray tracer, in this case you have other analytical geometries, then you definitely need this.
But if you scroll up a bit, you can see that it's doing it on the whole scene, I'm pretty sure.
Yeah, I
Yeah,
would.
in this particular case, it's not useful.
Yeah,
gonna
but
say,
this would scale to several.
You probably would want the LNOD texture inside of that return false down there, but it's always just a good idea to have your function return something at the end in case something unexpected happens and you somehow manage to reach the end without necessarily having a t greater than distance that gets hit in there, or something happens. Who knows what happens? You run through the loop before t is greater than distance, then you want to have something return at the end and just say, well, we never managed to reach a t that was greater than distance, but we'll just presume that it would have gone on forever anyways, just as a general programming thing.
You hit that case if you go past max iterations.
Yeah, exactly.
But if you do go past distance, then there is no skybox code, right?
Yeah, like I said, I would have added the skybox code in personally before the return false inside the for loop, but
it seems like the skybox should actually be outside if they're doing the thing where you could, like Leslie was saying, you could have multiple objects.
Right.
Like, I mean, it'd be interesting to have SDFs as one of the primitives in a ray tracer, right? And in that case, you would want to, update the distance like it does here.
Well, I guess,
Or
does
maybe this is doing some kind of minimum, I guess. Is it? Or is it not? This is weird.
I still don't get line 18.
It is weird too, because if you look at the previous code snippet, they pass in infinity for the distance. So I guess theoretically that branch shouldn't ever happen.
Okay.
Yeah, it should never be. Yeah, you should never be able to get a value greater than infinity, I guess. Because it's you're getting that just from adding the distance function value to the total distance.
What does trace ray return if you hit max iterations?
I think this one would just keep going. Or is there iterations? Is that used anywhere?
No, I mean, it doesn't return a
no.
bool.
Yeah, what does
It's
it
not
do? What does it
returning a
do?
bool in that case. Seems like a bug.
It's returning false
Yeah.
on line 23.
Line
It'll
23.
maybe fall out.
Oh,
yeah.
damn.
There you
Oh, shit. I thought that was the end of the function. Sorry. I thought line 21 was the end of the function.
Yeah, the indentation is confusing on
Okay,
12
got
there.
it. Okay, my bad.
Well, I guess
No.
so. I guess when you're wanting to do a secondary bounce, then you would set distance to be smaller. So I guess that actually makes sense, right? Because if you're wanting doing the secondary bounce, then you don't necessarily want to return the skybox if you like you've set the distance smaller and you don't reach and you get past that distance, then you don't necessarily know that you hit the skybox. I guess there could be other stuff in the scene.
Mhm. It seems like you really want to do material stuff outside of trace ray. Like once you've, like
Yeah.
instead of returning the color, you just return like a material ID or something and the normal and position or something, and then do the colors or the materials outside. I don't know.
I think that's a better way to do it. Yeah. Yeah, you get your values for your surface and then solve for what your shading is going to be on that with that given as input. Yeah, so then they talk about some like set operations on these different things. So how you can do intersection, subtraction. Let me find this other thing. I was actually using this very recently. They have a lot of really good set operations. I'll share it on the shit. I'll share it in the general channel on GPPM.
Yeah, it's so nice that this makes like constructive solid geometry operations like trivial.
Mm-hmm.
Like if you do it for like if you do it for like a regular ray tracer without this kind of stuff, or without ray marching on a sphere trace kind of thing, it's not so easy. Although it's still one-dimensional.
I think it is actually kind of the same operations in ray tracing, right? But you have to collect all the intersections and then do a min or a max.
No, I'm not sure.
That has to be the most unique URL I've seen in a while.
Yeah.
That's very, very different. The min and max in here is to combining the SDFs. It's like combining two pieces of geometry into some like larger geometry. It's very different from what we do in ray tracing.
That's true.
And
yeah,
in
like
fact,
in ray tracing, you're doing min and max on a t values, not the distance values. So
yeah, that's why like we can even plug in SDF into analytical. No, not analytical. We can put this into ray tracing. Like we can have a SDF primitive in it. They combine those two.
So I guess they're doing these set operations of two different functions. And then you can use mod logic on the floating point distances in the space. You can basically say have it repeat every x distance by giving me the remainder when you divide by that. It's the floating point modulo operator. It's the same like remainder type of idea, but it's to make the space repeat from 0 to n, whatever the modulo value is, and then have it repeat from 0 to that range again. So that's a cool way that you can have things instanced through space, and that's infinite to the whatever range your maximum distance is.
This is good for periodic tiling, but what if you want to do aperiodic tiling? Is there some trick for that?
So I've seen some stuff on Shader Toy, but you can use that same kind of like hash based on which repetition you're in. You can consider that on 1 repetition and 2 repetitions, 3, blah blah blah, by taking the integer division. You can get the whole number of repeats, and then you can get a hash value seeded by that x and y or whatever. You can do it on 3 dimensions, and then you can have some different behavior based on some seeded random number that's in there. So you can kind of like you can know the minimum distance for that that cell, and then maybe you can look at the neighbors too. So I don't know. There's ways that you can make that work. I think if you had different transforms based on that hash that was seeded from the position.
So you're talking about transformation, the next subject, like combining
yeah,
transformation with like the tiling on the hash of the remainder or something.
Idea, yeah. Doing something like that, yeah. Yeah, so rotating it, scaling it, whatever you want to do, I guess, as a as a way to change properties of it based on position there. Or maybe you wanted to get different surface behavior for different ones. You could return material ID from there as well. So. Blending, yeah, smooth minimums are cool because it basically it's kind of interesting. It basically it takes if you've ever seen metaballs, the sort of situation where they have smooth surfaces that blend into one another. This is kind of basically as the shapes become closer and closer together, they kind of the areas that have in the crotch of the spaces, they become lower and lower, and it basically brings that value down to 0, and it brings the surface out into like chamfer that surface basically. Yeah, so yeah, if you look at that document, Discord, yeah. They have a lot of these different types of intersection functions based on if we look at like this one, they have the up intersection round, and basically that's taking the maximum of what is it? Okay, yeah, I guess they're doing the plane intersection in one thing here. Or something. Or wait. Anyway, yeah. What it does is it creates a smooth a smooth surface where those two would just come together with a solid intersection. Like yeah, creating a smooth surface between them, or with different features based on some different use of those variables. Yeah, and then there's some interesting usage of it. I haven't actually looked at the implementation of that one. Oh, I guess it's not in the Interesting. Huh. Anyway, yeah, so there's a lot of different operations that there are there. Yeah, so there's some improvements on performance on the on that surface intersection, and some of them, like what I mentioned before, will only slow it down further. But there are ways to do better.
Can you explain the over relaxation thing? I don't understand how that.
I guess I'm not actually very familiar with it. I've never actually gotten familiar with how this works.
Sounds like you could make bigger steps than what the distance function tells you. Sometimes.
Guess I'm not really speculatively take larger steps.
Oh, they're overstepping, and if they hit, then or not if they hit, if like I guess
What
I
if-
explained.
What if there's a surface right there? Or
I think it's if the distance goes down, then they step backwards.
Yeah.
So if the distance is only ever increasing or equal, then they know they didn't hit anything. Like they know they didn't previously hit something too that they missed. So then if the distance goes down though, then they could have missed something. So then they step back a few steps.
Oh, awesome. Thanks for the explanation.
Yeah, that's cool. I might have to try that. That's cool. Yeah, because I've been using like a multiple of like 0.6, and that makes things like, that's for the fractals. You kind of have to do that. I'm wondering how this is at resolving fine detail.
I guess it should still be perfectly exact, I think, right? Because they do the backtracking.
Probably. And I think you could, I wonder if you could make this step like arbitrarily large as long as you have a sufficiently, I guess, relaxed, like condition to go back.
I guess you
If that makes
could,
sense.
I guess theoretically you could, if there was like a small bump in the ground in this picture, you could step completely past it if you go too big.
Yeah, but the idea is you raise the threshold, or I guess you lower the threshold for stepping back.
But I mean, you might not notice you have to step back because your step was so big that the distance didn't even go down, right? Because you just like shot way
But if you
past it.
completely miss the feature, right? Or
Yeah.
the bump or whatever.
I feel like there's like a point where you can't tell.
Yeah.
I wonder
Yeah.
if
That's why it says K, the maximum K is 2.
Okay, that makes sense. Yeah.
I do wonder if it actually helps all that much with things, because I know that when you have to do something like this, oftentimes you're going to have to add an if statement or something to break out of what was originally just a flat for loop of going through it really fast. And typically, I think I've tried some of these different things with the clouds. It actually made it slower when you had to like try some of these things, because you had to actually break out of the loop, go back, figure out where you needed to go back to, and have all this complicated logic versus just, a flat plain for loop.
I wonder, yeah, like the little, they talk about with that city scene below, they say it was a 25% faster, but I'd be curious if it is very, like, it must be really dependent on what your scene is. Like, imagine like with the city one, there's a ton of open space, so you might it might be worth it to skip all of that.
Yeah, I can see that.
But then like something like clouds or something, you're like, I don't know, maybe you're in it more often.
Yeah, I think I did remember that if I had like very few clouds, that it like helped a lot. But if I had a moderately cloudy day, then all of a sudden it would like really, it would murder everything.
Right. Oh yeah, so they say here, success doubles the step distance, failure doubles the number of evaluations. So picking the wrong number can either double your performance or halve your performance.
Yeah. That's interesting. I'm gonna have to try that. Yeah, bounding spheres. That's a good some sort of way to just say that some point represents the center of your object, and you know that the maximum extents of that object are at some distance. Then you can say, within this distance of that sphere, we consider it sufficiently far away that it's just the maximum the distance to that point. We're calling that the closest point in all directions, and call that good enough, because it's that same thing we were talking about before. It's as long as it returns a value that's lower to the distance than the it might not necessarily be the closest distance to it, but it's not lower than the closest distance to it, then you can kind of estimate the distance to that surface.
Is it common to do like a full-on BVH where you like have a bunch of like nested bounding spheres?
I'm not sure. I think that would be a cool way to do it. I laid out the scene earlier that it's got like railings and stuff, and I wanted to see if I could do any better by putting a box around two different sets of like 3 cylinders that were the railings and stuff. So I wanted to see if I could do some sort of bound around that. It might help. But yeah, I should try this over relaxation thing, because that would be like using 0.6 versus doing a number larger than 1. I'm not sure. I think that would be pretty significant speed up there.
And I guess like a bounding sphere might be pretty bad too if you're gonna have like long cylinders or something, right? Because the sphere could get massive, but if your geometry is actually thin, then
Well, and also, yeah, these are infinite basically, because they're just it's basically distance to a line, closest distance to a line.
I mean, you can probably adapt it to whatever geometry you happen to have. If you know you have lots of long spheres, then or long cylinders, you should probably make sort of bounding cylinder geometry.
right.
Yeah, maybe, or maybe a box would work. I mean, yeah, just do the maximum width and maximum on each dimension, because these are axes aligned. These particular ones are, I guess. So anyway, I could pretty reasonably do a box around it. But yeah, if I was and I was thinking about doing that for the whole section that I laid out so far, and then doing another section that's in a separate bounding box, so it doesn't evaluate unless it's in that box. And I think that might be an interesting thing to try.
I actually have a question. At what point do we switch over, and are we actually going from ray marching, and are we actually ray tracing instead?
So it's really just down to semantics. Like, this is kind of okay. You get an estimate of where you hit the surface, and the real distinction is it an explicit surface intersection, or is it an implicit surface that we've kind of taken a successive approximation until we're happy with how close we are.
Okay.
We're not doing recursive retracing with most like shaded toy stuff, but you certainly can. You certainly can do recursive retracing with them. It's just
Yeah,
extra
but we're
expensive.
yeah, it is actually very, very much. Yeah, and especially if you have a good BVH, yeah, it's a lot faster to do it just with triangles because and also you know that you're going to get the closest intersection point versus an estimate of it basically from the SDF. So anyway, that's yeah, something interesting, I guess there. Huh. And I guess maybe they're talking about recombining the two, doing explicit and implicit surfaces in the same scene. So you're basically taking the minimum of the two intersection points if they hit one or the other or both.
Okay, I just also think about this is like when we talk about bounds, if we have those SDF only contain small areas, it's really easy to have a bound. But if let's say we have this plane at the ground, then we basically have no bound. So it's very useful to split, I think from this perspective, split SDF into small pieces. And also maybe some of them can be just analytical shapes. Yes, I never thought about this before.
And this is also interesting. If you take that intersection with the plane first, you know your maximum ray march distance. And that can be fairly small for the close distances here right in the foreground.
Yeah, that's a good idea.
Like,
Yeah.
so you know that you can't exceed that distance for that pixel or that distance for that pixel, whatever it is. Yeah.
So it seems like the biggest performance problem with SDFs is like near misses. Like if you get really close to an object, you can take a lot of really small steps. And so like if you split stuff into, or if you bound box things, maybe you can skip things really quickly and only do the SDF when you get really close to something and there's a good chance you're going to hit it.
Yeah, so the tighter your bounding box would be the best situation. Yeah. I've seen a couple different ways to voxelize scenes, and what they do is they'll either store the closest distance per texel in a 3D texture, or they will keep the ID of the closest object, surface ID of the closest object in the scene, and then it can do it based on, closest per texel. And then it can evaluate the actual function for that object to get like say, all right, I'm closest to this based on every texel in this neighborhood was pointing to this particular object. Some identification value in there. Yeah, so that's a way that you could do meshes even if you kept that value for each texel in the thing. You could potentially approximate a mesh or something like that. So there's a couple cool things you try. Actually, if you did, I was just thinking because there are as uint and as float functions in shading languages, so you can encode those in bits and then put them into texture, and then decode them in the whatever is doing the final testing there. So you could tell it multiple different IDs. So you could have it check against multiple shapes, or if you had indexed triangles or something like that. It's another thing you could have that point to. Anyway, yeah, a lot of different ways that you could use information like that. You could have it keep lighting information. Actually, you could have that mapped to some location in some storage, and then you update whatever lighting calculations you did in that area, and then report back, kind of thing. Store back to your texture if you have read write, kind of a thing set up there. So that's kind of like an irradiance caching kind of idea. Anyway, those are some different ways you can use that type of information. So I guess they're doing a couple different things here. And there are endless examples on Shader Toy. Yeah, you just pretty much anything you see on Shader Toy is going to be this kind of stuff. So yeah, that's everything there.